Welcome PPL students to this explainer. If you're gearing up to write your ground exam, you're in exactly the right spot. We're skipping the fluff today and tackling some of the most highly testable concepts you're going to face: aircraft weight, balance, and the all-important center of gravity. Let's get to it.
You might hear this kind of dangerous rule of thumb floating around the hangar. If I have 3 passengers, I can load only 100 gallons of fuel. 4 passengers, 70 gallons. Well, here's the hard truth. Guessing like this is a guaranteed way to fail your exams, and more importantly, it causes real-world accidents. You just can't assume 3 passengers are always going to weigh the same. Which brings us to a golden rule: compute everything. Unequal load distribution causes accidents. And remember, aircraft weight and balance data isn't valid indefinitely. Over time, planes get repainted, equipment is upgraded, maybe some heavier new avionics are swapped in. Because of all these modifications, you absolutely must do a fresh computation of all loaded items. Don't guess, actually weigh the baggage. Doing the math ensures you're respecting the exact limits of your specific aircraft on that specific day.
Now, let's look at the center of gravity, or CG. The textbook definition you need to burn into your memory is that the CG is the exact point where the aircraft would balance if you could somehow suspend it in midair. This one invisible point critically affects stability, controllability, and performance. In fact, most of the tricky aerodynamic questions on your ground exam are going to trace right back to exactly where the CG is located.
So picture the physics of your aircraft in flight like a giant teeter-totter. The gross weight of the airplane pushes down right at that center of gravity. Just behind that point, the center of lift from the wings pulls the aircraft up. Now, because the lift is pulling up behind the heavy CG, the nose naturally wants to pitch down. To stop the plane from just completely flipping forward, your tail has to act as a counterbalance, exerting a downward aerodynamic load to keep everything perfectly leveled out.
The crucial thing to understand here is that the position of your CG completely dictates this mechanical battle. If your CG is loaded forward, meaning closer to the nose, that nose-down pitching tendency is much stronger. So your tail has to fight way harder, requiring a heavy downward force to balance the plane. On the flip side, an aft CG, where the weight is loaded further back toward the tail, needs significantly less downward tail force to maintain level flight.
Section 1. Forward CG. Stable, but heavy.
Like we just saw with our teeter-totter analogy, a forward CG makes the nose want to drop heavily. To counteract this, you need increased stabilizer deflection to hold the nose up. Think about what that actually feels like for you sitting in the left seat. It translates directly to higher, heavier elevator control forces on the yoke. You're physically working harder, constantly holding greater back elevator pressure just to keep the nose on the horizon. It's incredibly stable for sure, but it handles a bit like a flying brick.
Section 2. Aft CG, fast but unstable.
Believe it or not, there is actually a silver lining to having your weight loaded in the back. Because an aft CG requires less downward tail deflection to overcome that nose-down pitch, you basically have less airplane surface fighting the oncoming air. You get to fly with a smaller angle of attack and significantly reduced drag. The performance result here? The aircraft actually cruises faster and a whole lot more efficiently. But hold on, because that extra speed comes at a dangerous, highly testable cost. As the CG shifts further and further rearward, your angle of attack naturally increases, and overall wing stability decreases. Eventually, you hit this terrifying point where the wing and tail contributions perfectly balance out. We call this neutral stability. Any further aft movement from this point makes the aircraft entirely unstable. If you hit a bump of turbulence, the plane won't correct itself. It'll just keep pitching up until you completely lose control.
Section 3. Elevator control and stalls.
Now let's bring this physics lesson to a life-or-death reality: stall recovery. Going back to our forward CG scenario, remember that it creates a heavy nose-down pitching tendency. As you pull the power back and slow the aircraft down towards stall speed, that nose-down force is going to feel even stronger. Your elevator has to constantly oppose this pitch, demanding massive amounts of back pressure on the yoke just to keep the nose up as your airspeed completely bleeds off.
So here's the critical question you'll probably see on your exam. Can your elevator oppose a nose-down pitch in a stall if your CG is pushed beyond the forward limit? The answer is a terrifying no. If you load too far forward, you might actually run out of elevator authority entirely. You'll pull the yoke all the way back into your lap, and the nose simply won't come up anymore. This makes stall recovery incredibly difficult, and executing a proper landing flare nearly impossible. You'd basically be arriving nose first to the runway.
Before we wrap up,
I actually tried to explain the concept of center of gravity to my non-pilot friend yesterday, but unfortunately, the whole thing just went right over his head. Seriously though, as a PPL student, you know this topic carries a ton of weight for your upcoming exam. Understanding these concepts won't just help you pass your written test, it'll keep you and your future passengers safe up there. If this explainer helped you prep, please hit that like button and subscribe for more structured study sessions. Keep hitting the books, but I'll leave you with this. The next time you're loading bags into your Cessna, ask yourself, is your weight distribution keeping you perfectly stable, or are you pushing the absolute limits of your control?